Gold is rare. So rare that if you gathered every ounce ever mined in human history, it would fit inside just 3 Olympic swimming pools. But that shimmering metal on your finger didn't start on Earth. It began in an explosion much bigger than a supernova, so violent it reshaped the periodic table itself. Gold is one of humanity's oldest obsessions, a symbol of wealth, power, and stability. Yet behind its beauty lies one of the most fascinating origin stories in the universe. Unlike carbon or oxygen, gold isn't made in stars like our sun. It needs a special kind of catastrophe, one that crushes atoms together with unimaginable force. To understand how gold exists at all, we have to go back billions of years, to the cosmic forges where matter itself was born. So this story starts at the beginning, not of gold, but of elements. When the universe began 13.8 billion years ago, there were only 3 elements: hydrogen, helium, and trace amounts of lithium. That was it. No carbon, no oxygen, and certainly no gold. Everything else, every atom heavier than lithium, had to be forged later, inside stars. Stars are element factories. They shine because they fuse hydrogen into helium, releasing energy. As they age, larger stars burn through their fuel and start fusing helium into carbon, carbon into oxygen, and eventually into heavier elements like silicon and iron. But that process has a limit. Iron. Oops! This iron. When a star tries to fuse iron, it stops gaining energy. Instead, it consumes it. That's the end of the road. The star collapses under its own weight and explodes as a supernova, one of the most energetic events in the universe. For decades, scientists thought these supernovae were where gold was made. It made sense. They're powerful enough to hurl new elements into space, seeding the universe with heavy atoms that will one day form planets and people. But there was a problem. Even supernovae couldn't explain how much gold we actually see. By the early 2000s, astrophysicists noticed a mismatch. Computer simulations of supernova explosions showed they could make small amounts of heavy elements like silver and tellurium, but not nearly enough gold. The conditions simply weren't extreme enough to produce the heaviest stable elements on the periodic table. That's because making gold requires something special, a flood of neutrons. See, when lighter atoms fuse together, like hydrogen or helium, they produce energy and release light. That's fusion. But to create elements heavier than iron, you need a different process, one that doesn't depend on heat alone. You need to smash atomic nuclei with neutrons faster than they can decay. This process is called the R process, short for rapid neutron capture. It's a kind of cosmic assembly line. An atom captures a neutron, then another, so quickly that it doesn't have time to fall apart. Each new neutron increases its mass until it stabilizes as a heavier element. Gold sits near the end of that line. To make it, you need an environment flooded with neutrons, billions of them, slamming into atomic nuclei within fractions of a second. So, where in the universe can that happen? In 2017, we got our answer. That year, the LIGO and Virgo observatories, 2 giant gravitational wave detectors, picked up a signal that wasn't from a black hole, but from the collision of 2 neutron stars. When 2 of these dense objects spiral toward each other and collide, they release a burst of gravitational waves, visible light, and, crucially, a storm of neutrons. Telescopes around the world watched as the light from that collision, known as GW 170817, changed color over several days. It began blue and faded to red, a signature that matched predictions for the radioactive decay of newly formed heavy elements. In that single event, scientists estimate that around 200 Earth masses of gold and platinum were created in just seconds. That discovery changed everything. For the first time, we had direct evidence that neutron star collisions, not ordinary supernovae, are the main cosmic factories of gold. The collision of neutron stars, called a kilonova, shines as bright as 100 million suns, but it fades quickly, over days, not months, leaving behind a black hole or an even heavier neutron star. What's left are clouds of newly forged metals expanding through space, eventually mixing into future generations of stars and planets. That's how gold arrives in the universe, not in steady streams, but in rare, spectacular bursts. The gold that formed in one of these collisions billions of years ago has traveled far. Over eons, that stardust cooled, condensed, and joined gas clouds that formed new stars, including our Sun. When the solar system began forming 4.6 billion years ago, some of that ancient gold dust got trapped in the swirling disk of material around the young Sun. As planets grew, gold was incorporated into their cores and crusts. On Earth, most of the planet's gold actually sank to the core early in its formation, drawn downward by gravity when everything was still molten. That means the majority of Earth's gold, by mass, lies thousands of kilometers below our feet, far beyond our reach. The gold we can mine today probably arrived later, delivered by asteroids. Around 4 billion years ago, during a period called the Late Heavy Bombardment, Earth was pummeled by debris left over from the early solar system. Many of those asteroids carried metals from earlier star systems, including gold. Those impacts seeded the crust with the precious metal, creating deposits that humans would eventually discover, melt, and shape into coins, crowns, and circuitry. Every atom of gold on Earth was born in an event so extreme that it defies replication. Humanity can synthesize tiny amounts of gold in particle accelerators, but it takes more energy than the gold is worth. Nature's method, the R process in a neutron-star merger, remains the only true way the universe makes it. That scarcity is part of why gold is so valuable. Across cultures and millennia, humans have recognized its resistance to corrosion and its enduring luster. But on a cosmic level, its worth is also symbolic, because it represents the extreme violence and creativity of the universe itself. Gold is a fossil from a cosmic explosion, and it isn't limited to Earth. Meteorites often contain traces of gold. The Moon and Mars likely hold significant quantities too, relics of the same early bombardments that delivered gold to Earth. That's why future space missions are eyeing asteroid mining. Some metal-rich asteroids could contain tens of billions of dollars worth of gold and platinum. One, called 16 Psyche, may be the exposed core of an ancient protoplanet dense in metals. NASA's Psyche mission, launched in 2023, aims to study it up close. If asteroid mining ever becomes practical, it could change our economy. But it might also change how we think about rarity. Because what feels rare to us is, in cosmic terms, just another byproduct of stellar death. For centuries, alchemists tried to turn base metals into gold. They never succeeded because the transformation they sought doesn't happen in a laboratory. It happens in dying neutron stars. The universe itself is, so far, the only true alchemist. Thank you for watching Into the Loop. If you enjoyed this journey through cosmic chemistry, don't forget to like, comment, and subscribe for more stories about the universe that made us.